Okay, welcome everyone. This is office hours for the Evolutionary Robotics MOOC Ludobots. It is also the office hours for the University of Vermont course CS206, Evolutionary Robotics. If you're taking this course online or you would like to take this course online, you can start at any time at the MOOC homepage, reddit.com/r/ludobots. I will be online for the following hour. It's currently 3 p.m. Eastern Standard Time on Monday, March 20th. Like I said, I'll be online for the next hour or so. Please ask a question at any time. I'm happy to answer it. Any question about material from the course in particular, or any general questions about robotics or AI, and I'm happy to try and answer them. What I'm going to do today, while I'm waiting for questions, I will walk you through the implementation of multi-objective optimization, otherwise known as MOO. Multi-objective optimization is useful when you are trying to optimize something. In our case, we're trying to optimize robots to achieve more than one objective at a time. As we're going to see today, we're going to try and evolve robots that succeed at one objective, which is to move as quickly as possible. The second objective that we're going to add is that we want our robots, while they're moving, to not flip over or not jump or not fall to the side. We want them to maintain contact with the ground as much as possible. So we're going to select not just for speed, but also for stability. Okay. 2 weeks ago during office hours, I implemented, I laid the groundwork for multi-objective optimization by implementing a steady state evolutionary algorithm. If you want to watch me implement MOO, you can go ahead and do so. If you're following along with me, you might want to go back and watch me implement a steady state evolutionary algorithm, and there's the URL for that. Okay, so where did we get to last time? Well, last time, as I mentioned, we implemented a steady state evolutionary algorithm. Let me just clarify this a little bit so it's a little easier to read. They're basically four steps. See, my numbering here doesn't quite work. Okay, there we go. There are basically 4 steps to a steady state evolutionary algorithm. Create a population of individuals, which in our case are robots. So we have a population of random robots. We evaluate each individual in the population, and then we run our steady state algorithm for a fixed number of iterations. This could be 10 or 1,000 or 30 hours. It doesn't really matter. And at each pass through this iteration, we reach into our population. We choose 2 individuals at random, and we compete them against one another. We determine among those two in that pair who is the winner and who is the loser. Last time we chose the winner based on the one that moved faster than the other. We used a uni-objective criterion for determining who wins and who loses, which is simply speed, who moves faster. So we make a copy of the winner. We make a mutation of that copy. So, and then we replace the loser with the mutant. So in essence, the winner wins the competition, the loser dies, and the winner has the opportunity to produce an offspring. We then evaluate the mutant, and we then choose 2 new individuals and repeat this process for however many times we like. And when we're done, we then pick the best individual in the population and we watch it. That's the steady state algorithm. We're going to make a change to just one part of the steady state algorithm today, which is step 3B here. So when we pick our 2 individuals at random, we're going to determine, not based on just a single objective, but on 2 objectives, who is the winner and who is the loser. Okay, so how do we actually determine this? Well, to do so, I'm going to do a little bit of work at the whiteboard here. Let me just make sure that you can see. We're going to have to compute these 2 objectives for all of the individuals in our population. So, assuming that we can see the board okay. Okay, let's have a look at what this is going to look like. Last week, as I mentioned, we just had this single objective, which was speed, or how far the robot traveled in a fixed time period. We're now going to add our second objective, which is stability. So how stable is it while it's moving? Okay, so we've got speed on this axis here and stability on this axis here. And you'll remember that at the beginning we create a population of random individuals and then we evaluate each of those individuals. So when we evaluate each individual, we're going to determine the speed of that individual robot and its stability while moving. So stability we're going to define as how much time it's able to keep at least 1 foot on the ground. So the robot is determined to be unstable if it jumps and all 4 feet are off the ground, or if it tips on its back and all 4 feet are up in the air. Okay, so that's stability, and we'll define that in more detail in the code as we go. So let's take one of our individuals. Let's assume that it moves relatively slowly, but it's relatively stable, right? So we can represent now an individual. We can represent now an individual in the population by a position in this two-dimensional plane. Here's one individual which moves relatively slowly but is very stable. Perhaps this is the robot that just stands still. Imagine another robot out here at a different extreme which moves very quickly but is very unstable. Maybe this robot is jumping or jumps over and flies on its back and lands on its back and moves that way. Okay, remember we have a population of individuals like this. So we have, when we create our random individuals, we have a population that looks something like this. And assume for the moment most of the points are going to be in the lower left because at the beginning we're probably going to have robots that move relatively slowly and maybe are somewhat stable or not so stable. Okay, that's step 1 and step 2. Step 3 in our algorithm is we're going to pick 2 individuals at random. Let's imagine we choose this individual and we choose this individual. So that's step 3A. Now we come to step 3B, which is who wins and who loses here. Well, let's consider these 2 individuals. I'm going to call them individual I and individual J, just for the moment. And we can see in this case here that I is slower than J. So here's the speed of J, and here's the speed of I. We can see that I is slower than J. And we can also see that J is more stable than I. So J is dominating individual, is dominating I, right? It's better in terms of both objectives. So in this case, the situation is pretty clear. J is the winner, and I is the loser. And what do we do with the loser? The loser is deleted. J gets to make a copy of itself. That individual is then mutated, and we then evaluate that new individual. And let's imagine that that individual lands here, and we'll call this individual J prime to indicate that it's a mutant, or it's an offspring of J. Okay, so that's one possibility. Here's another possibility. All right, here's our population. Let's imagine now that we select this individual and this individual. We'll call this one I, and we'll call this one J. Who's the winner and who's the loser in this case? Well, we can see that J is faster than I, so it's better in terms of this objective. J is better in terms of this objective, but I is more stable than J. So now, in this case, one of the individuals is better at one objective, and the other individual is better at the other objective. So in this case, neither dominates the other, right? So in this case, we can't determine a winner and a loser. Neither is better than the other. So in this case, we're going to have to change our algorithm and just assume that the matchup here, the competition, is a tie. Neither wins, neither loses, which means neither one dies and neither is able to produce an offspring, is able to produce an offspring. So let's alter our code a little bit here. So we're going to visit line 3B. We're going to visit line 3B, and we're going to, the winner is better on both objectives. Okay, choose two individuals at random. Let's actually add something in here. Let's call these two individuals, choose individuals I and J at random. And if I dot speed is greater than J dot speed, so if I is faster than J and I dot stability is greater than J dot stability, so I is both faster than J and I is also more stable than J, then winner equals I, loser equals J. Okay. What about the other situation? What if J dominates I? Well, it's just the opposite situation. So now if J is faster, hi there, sorry, I'm recording live. Thank you, no problem. Okay, if I is faster than, if J is faster than I, and J is more stable than I, then in this case J dominates I, and the winner is J, and the loser is I. Finally, if neither is the case, which means that I is better on one objective and J is better on the other, return, do nothing. Right? We're not going to enter in this. We'll go back to the beginning of the iteration and continue. Okay, so this is the code that we're going to add now to determine the outcome of this competition. Let's see for a moment what happens if we do. So let's go back to our two objectives now. We have them here. Well, what happens? So eventually, we would imagine that if we're always choosing the winner as the one that is to the right and above the loser, we're eventually going to lose individuals that are lower and to the left. And what we're going to expect is points are going to move up and to the right. And eventually, we're going to get some robots up here, which are both fast and stable. Right? That's what we're trying to do. Okay, so let's implement this in code now. Okay, so let's go back to our steady state algorithm for a moment and have a look at the code. Okay, so this is, if you followed along last time, you should now have a file called mu.py. And let's go to the bottom. Here's our step one, initialize random individuals. Here is evaluate all of those random individuals, and now we're going to iterate for some number of iterations. We're going to select a pair and compete them against one another. We're going to print all the individuals in the population, and then we're going to show the best one. So let's actually just run this code to remind ourselves what happens. I'm going to look at num iterations for a moment, which is in constants.py. When we did this before, we did it for 1,000 iterations. Let's just change it to 10, so this will run quite quickly, and we can see what happens. Okay. So when we run this, for 10 iterations, we get something that looks like this, which you can see is moving relatively quickly and then stops. Let's run it for a little bit longer, see if we can get something that moves a little bit faster. Let's run this for 100 iterations. You'll notice we have a population of, I think, 50 individuals, and here's our iterations, 80, 90, and at 100, we now look at the best robot. Okay. So you can see this robot moves pretty quickly, but it's sort of unstable. It's sort of jumping around quite a bit. This is why we're adding the second objective, to keep our robot firmly on the ground. Okay, right, so we have a population of 50 robots, and we perform this competition 100 times. Let's speed it up while we're adding this new code. Okay, so let's go back to our pseudocode for a moment. Here we are here, choose two individuals, ing at random, and now we're going to implement steps 3b through 3d. Okay, so let's go back to this. We're going to make changes in our compete one against another here. So let's find that function. Okay, so here we go. Here's where we pick two individuals at random. We make sure that the second individual is not the same as the first individual. If so, we pick another one. When we get to this line, we know we've picked two different individuals in the population. And we set the winner and loser depending just on their fitness, which in this case is speed. So let's change this now to the following. If I dominates individual J, then the winner is clearly this. The winner is I and the loser is J. Otherwise, if it's the opposite case, if individual J dominates individual I, meaning J is better than I at both objectives, then the winner is J and the loser is I. Otherwise, return, right? We're not going to continue on and carry out the competition. Okay, so now we've introduced a new function called dominates, and that's associated with pop I. And pop, to remind ourselves, is an empty dictionary. And when we initialize this dictionary here, we set each entry in the dictionary to be an instance of individual. So we now need to go to individual.py and add this dominates function. Okay, so def dominates. At the moment, let's just say that no one ever dominates anyone else. So no competition is ever going to occur. So let's go back to compete. Okay, so what have we done now? So we picked these two individuals. Neither can ever dominate the other, because whenever dominates is called, it just returns false. So there's never a winner here. There's never a winner here. We always just return from this function, compete one against another. So let's go back to the main function. We initialize a population of random individuals. We evaluate each individual in the population. We then try a competition. Every competition fails. We print out the population, and at the end we show the best. So because there's no competition, no new individuals are ever created here. So when we show the best, it's simply going to be the best from the initial random population. Let's check that that's the case. Let's run our code. We've got a few typos here. Line 51. Aha, missing a colon. We still have a problem here. We have a missing bracket. Yes, that is true, we do. Let's run our code again. We create our initial random population, and we forgot that we need to send into this dominates function the other individual that we're competing against. Okay, so let's go back to individual.py, find the dominates method, and we have to remember to pass in the other. So self, remember self is self, and other is the other one that's being computed against. Okay, so this is the best individual in the initial random population, which doesn't do too bad, but doesn't move that quickly either. Okay, so there we go. Let's go in and change that now, individual.py. So dominates is eventually going to be that self has to be better in terms of both objectives. But let's for the moment just keep this simple. If self.fitness is greater than other.fitness, then self dominates other. Otherwise, it doesn't. So we've really just added in what our original steady state evolutionary algorithm did, which was to compete these two individuals just based on fitness or speed. So now our code should do pretty much what it did before. We evaluate our initial random population and perform several iterations, and this is our best at the end. Here's a great example of something that is not very stable. Okay. So now we need to define, oops, sorry. We know that fitness is speed at the moment. We need to now create this stability measure. How are we going to compute this stability measure? Well, what we're going to do is compute stability as how many times the robot was able to keep its feet on the ground. So our robot is evaluated. If we go to the constants file, we can see that the robot is evaluated for 500 time steps. So we're going to look at each of the 500 time steps and look to make sure how many of the 4 feet are on the ground at that time. How are we going to know that? Well, we already know that actually because our quadruped with its 4 legs has a touch sensor, 1 in each of the 4 feet. So if the touch sensor returns 1, that means that foot is on the ground. 0 means it's not. So we actually are going to take a matrix which has 500 columns and 4 rows, and each element in that matrix ij indicates that foot j was on the ground at time step I. Stability is going to be simply the sum of that matrix. So if the robot keeps every foot on the ground for each of the 500 time steps, every element in that 500 times 4 matrix is 1, and the sum is going to be 500 times 4 is 2,000. If the robot was able to magically levitate for every time step of the 500, no touch sensor would ever fire, and that 500 times 4 matrix would be filled with elements equal to 0. And the sum of all of those elements would be 0. Stability equals 0. Okay, how do we get at that information? Let's have a look at robot.py. To remind ourselves, our robot is made up of a series of objects, a series of joints, sensors, neurons, and synapses. We're interested in the sensors, which are down here. So we can see in sensors here, I'm going to just delete some of my unused code here so it's not confusing to you. We're going to place 1 touch sensor in each of the feet, and the feet have ID 5, then 6, 7, and 8. That's why it's 5 plus t. So we're putting 4 touch sensors, 1 in each of the 4 feet, and a 5th sensor in the main body, which is the light sensor. So the robot can sort of sense how close it is to that light source that's out in front of it. So we want to collect the information from the first 4 sensors. Okay, where do we get that individual? Where do we get that information? Let's go back to individual. And we are looking for compute fitness. So this function is called when the simulation finishes. So we wait for the simulation to finish and then put all of the information into we put all the information, sensor data into here. See, we're collecting the information of the 5th sensor, and we're going to take the very last element in that vector. So what is the light value of the light sensor at the last time step? Basically, how close does it get to the light? That's really how we're measuring distance or speed. So let's change this sensor data to light sensor data, which is what it is. That's fitness. Let's get the touch information now, touch sensor data. Okay, so that's sensor ID equals 0. This S equals 0, we won't worry about that for the moment. We can just leave that alone for now. Touch sensor data. And let's see what that looks like. Print touch sensor data. And after it's printed out that information, let's just exit the program. We just want to see what this looks like. Okay, here we go. So you can see that we got back a vector that has 500 elements in it. And you can see that they're 1 or 0. This is for the first of the 4 feet. And we can see that at the first time step, that foot was in contact with the ground. At the second time step, it was in contact with the ground. And then it lifted that foot off the ground. Let's, for fun, just measure stability as the sum of this vector. We're going to select for robots that are able to drag or keep 1 foot on the ground for as long as possible. So we're going to set stability to be simply the sum of all of the entries in this vector. We'll go back and change stability to be all 4 feet later, but for fun, let's just do one foot to start with. Okay, let's go back to compute fitness. Here's our touch sensor data. So we're going to say self.stability is equal to the sum. We're using NumPy's summing function, which operates on vectors and matrices, to this. And let's actually make sure that we got it. Let's actually print the stability. So we're going to print out the vector, and then we're going to print out an integer, which would be the sum of all the elements in that matrix. NumPy, I'm sorry. Okay, well, this was an interesting robot. We can see that it kept 1 foot on the ground, and then it lifted it off for the entire rest of the evaluation period. Maybe it flipped over, maybe it just kept it off the ground, who knows. This is clearly a robot that, at least in terms of this foot, it was very unstable. Let's run it again. We get a different one. This one is much more stable. It keeps its foot on the ground for a much longer period, or for a larger fraction of the evaluation period. Okay, just as a reminder, if you have any questions, please feel free to ask at any time. I'm in the process of coding up a multi-objective optimization method. Okay, so let's go back to individual.py. And just to really make sure we know what's going on here, let's print the fitness of one individual. So we've computed the fitness and the stability, the fitness and the stability of this robot. Let's print it out. So for the first individual in the population, this was its speed, and this was its stability. We run the program again. We get a different individual. It's a little slower and less stable. Yeah. Okay. Okay. So we now have that information. Let's turn off the printing of it. Okay, so now let's go back to mu.py. So now when we evaluate all the individuals in the population, each individual has a fitness or speed, and it has a stability. Now let's go back to our competition and remind ourselves that we're working on dominate. So individual I can only dominate individual J if its I is faster and more stable than J. So let's go into and let's change the dominates function. Okay, so here's the first objective. Let's add in the second objective. So as long as self is faster than other, and self dot and self is more stable than other, does self dominate the other? Okay. You'll notice that before we were also printing out the ID of each individual and its speed. Let's also print out its stability. So let's change that. Where do we do that? Print all here, def print all. Okay, so you can see we print for each individual in the population. We print its ID and its fitness. Let's also print its stability. Okay. Let's just have a look at the initial random population for a moment. So I'm commenting at all the rest of the code, and I'm going to print everyone after they've been evaluated. So create a population of random individuals, evaluate every individual in the population, and then print them all out, and let's see what they look like. Let's also reduce the size of our population to 20, so we can see this a little bit better. Okay, so here we go. Here are the 20 individuals. We can see that their speeds are all printed out and their stability. Here's one that's quite stable. It kept its first foot on the ground for 426 of the 500 time steps. This one was very unstable. It kept its foot on the ground for only 43 time steps. Here's one that was very unstable, another one that was very unstable, and so on. Okay, let's go back to our main function. Let's run a few iterations. And I'm just going to leave this turned off for the moment. We're not going to look at the best one yet. We're going to just print what we see. Okay, so what happens when we run our code now? Well, we just ran it for 10 iterations. And a little hard to see, but I think things are a little more stable. Let's run it for much longer. Let's do 100 iterations. And let's see whether on average speed and stability increases. Can see that definitely stability has gone up now. Most of the individuals are keeping that first foot on the ground for most of the time. Let's see what that actually looks like now. Let's show the best one when we're done. Okay. All right, a little difficult to see what happened in that case. That one was playing back the fastest one, which was, I think, this one. And you can see that it's keeping one foot on the ground for half the time, so it's not doing that great. Better than before. It's a little hard to tell which foot that actually was. Let's increase our population size a little bit. See if we can really get this running. Okay, who's the best one now? Let's see, 0.16 seems to be the best so far. Yes, this one. Also keeps its foot on the ground for only half the time. Again, a little hard to tell which of those feet it is. Probably, hard to say. Okay, let's try and run this for a little bit longer. See if we can get something that is both faster and more stable. Okay, so this is running to 500 now. We'll give this some time. You can see as it's running, you can see changes going on in the population here as we go. We're tending to get things that are quite stable, but seem to not be moving very quickly. And things that are a little bit faster, like individual 3 here, is keeping its foot on the ground for about half the time. So there's clearly a trade-off between speed and stability, which is sort of to be expected. Okay, but not bad. We're not getting something that's jumping around all over the place. It's definitely much more stable. And if you don't believe me, let's turn off that objective and see what happens. So let's go back to dominates here. Let's remove the consideration of both objectives and go back to just considering one objective. Okay. So now we're not really taking stability into account, just speed. Let's run the code again. Okay, we're going to 500 again. So you can see, even just looking at stability, there's lots of 200s and 300s in here. And keep running. Some very low things here. Very unstable things here, which we didn't see before. Let's see how we do. This looks like one of the faster ones here, very unstable. Let's see what this looks like when we get to 500. We're getting things that are definitely faster, but less stable because we're only considering speed. Okay, so before I play this one, let's see which one we're going to watch. Here's 177. I think that's the best one. Oh, no, 183 is better. Actually, it's relatively stable. Not a good example of the point I'm trying to make. Okay, so this one is not much less stable than what we got before. Okay, let's improve our definition of stability by taking into account not just the first of the 4 feet, but all 4 feet. So let's go back to individual.py and go back to the dominates function, and we want to again consider both speed, which is fitness here, and stability. Okay. And we need to go back to where we actually defined stability, which was here, right? Okay, so we're going to iterate over all 4 feet and add it to our stability measure. So let's first set it to 0, and then for t in range 0 to 4, so for each of the 4 touch sensors, for each of the 4 touch sensors, get the touch sensor data, sum up that touch sensor data, and add it to stability. Okay, now we're going to do all 4 feet. Let's see what happens now. Okay, obviously you can see the numbers have increased because now we're summing over all 4 feet, and we're trying to get the robot to drag or keep all 4 feet on the ground as much as possible. And you can see what's happening, right? Our robot is going a little bit slower because it's trying to keep all 4 feet on the ground. All right, definitely much more stable, keeps all 4 feet on the ground, much lower to the ground but moving relatively slowly. Let's see if we can do a little bit better by running this for 1,000 iterations rather than 500. So in multi-objective optimization, we are always trying to strike this balance between antagonistic objectives. So basically increasing one, like going faster, tends to mean you need to take your feet off the ground. And similarly, by trying to be more stable, by keeping all feet on the ground, you go a little bit slower. So we're trying to get evolution to find a good trade-off between these 2 elements. Okay, let's see how we do here. Something that's keeping its feet on the ground for a fair bit of time and moving relatively slowly. I'm not sure that that was actually the best one. Let's just check our code here. Show best. We want to find the best one. Yeah. Felt like that one did not quite move as far as before. Let's try it again. Okay, you can see how it's definitely keeping much closer to the ground. Maybe we're being a little bit over conservative with our definition of stability. So let's assume now that we're not going to force the robot to try and drag all 4 feet on the ground. What we are going to do is ask it to keep at least 1 foot on the ground at all times. So we're going to use the touch information again, but we're now going to look at each time step, and we're going to look at each of the 4 touch sensors. If all 4 are equal to 0, that's bad. That means all 4 feet are off the ground. The robot has jumped, and that's going to count against stability. But as long as 1 or more of the 4 touch sensors are fired during that time step, things are okay. So we're basically going to look at, we're going to go across the 500 rows, or sorry, we're going to go across the 500 columns and look at each of the 4 rows and sort of do a row sum. So let's go back to individual.py and have a look at stability here, where we define it. So let's actually create a matrix now. Let's create a matrix now called touch sensor data. And this is going to have 4 rows and 500 columns. Let's just make sure we've created an empty matrix first. All right, there we go. So there's our 4 rows and 500 columns. Looks good. Okay, we're going to iterate over each of the 4 robots, and we're going over the 4 touch sensors, and we're going to set the 10th row to that information. And I'm just going to put all that information in there and then print that information to make sure we got it all. Okay, so now we can see we've got the touch information for the 1st foot, 2nd foot, 3rd foot, and 4th foot. And we're going to look at each column and make sure that its sum is at least 1. We're going to sum each column, and as long as the sum is greater than 1, that greater than or equal to 1, that means at least 1 foot was on the ground during that time step. Okay, so let's see. Row sums, or sorry, column sums equals. Now we need to figure out how to get that information. Let me just look that up for a moment for you. Okay, so we're going to sum things again, and we're going to sum things for this matrix, and we're going to use axis equals 0, and when I print column sums now and exit, we should see now a single vector of length 500 with the sums of each of the columns. All right, looks good. So we can see at the first time step, all 4 feet were on the ground. At the second time step, 2 of the 4 feet were on the ground. But there was periods here when all 4 feet came off the ground. This is what we're going to penalize the robot for doing. Okay, so we now need to column thresholds. We're going to take column sums and threshold it. And I am not quite sure how to do that. So I'm just looking that up now. Okay, we're going to use a function called, apparently, numpy.clip, which is going to clip things that are outside of a given range. And we're going to give the matrix, and we're going to clip things to 0, 1. think this should work. So we're going to print the column sums, and we're also going to print the column thresholds to make sure that this actually worked. It's got an error there. Hold on one moment. We set the lower threshold to be 0 and the upper threshold to be 1. Yes, I believe that's right. Okay, let's try that again. Okay, so we can see, here's our original. We can see up until this point, there was at least 1 foot on the ground and then 0. And if we look down here, we can see exactly. So now column thresholds tells us for each of the 500 time steps whether there was at least 1 foot on the ground. And our final step is just going to be to sum these. We want to make sure the robot keeps at least 1 foot on the ground for as many time steps as possible. So last thing is to print the NumPy, the sum of column thresholds. Actually, let's give this a name. Number of time steps that the robot kept at least 1 foot. Actually, let's just use stability here, because we know that's what we want. So self.stability equals numpy.sum of column thresholds. Okay, and let's just print that one and see how we did. Okay, so here's a robot that was relatively stable, and sure enough, we get a number that's pretty close to 500. Okay, I think we're in good shape here. So we've now redefined stability, and we're ready to go. Let's run our code again, and let's see how we do. So we're not being as strict now with stability, and you can see already it's relatively easy for the robot to get a score that's near 500. For most of these, it's keeping at least 1 foot on the ground. All right, a little bit of ballet there. Maybe we want it to be at least 2 feet on the ground, but that's not too bad. You'll notice that it's skipping generations here, and or skipping iterations. Remember, it's skipping iterations because a lot of the times the competition between pairs of individuals fails. So it's actually going a lot faster than before. Okay, let's do the following. Let's make another change. You can see that we compete against one another. Let's stay in this iteration until there is a successful domination, there is a successful replacement. So we go back here, we can see let's return false, which means there was no outcome of the competition. No individual was produced. If we get this far, we know that a new individual was produced. So let's go back to compete, and let's say offspring created. So now offspring created will be true if this competition yielded an offspring, and it'll be false if it didn't. And we'll just say while offspring created equals false, keep trying to perform a competition. Yeah. So now we're ensured that for each iteration there is a new individual in the population. Okay, you can see we're stalled out here now at 2 because it's not finding a pair of individuals where one dominates the other. Okay, let's make sure that this is the case. Oh, we have a mistake here, sorry. Offspring, we have to reset this. Offspring created equals competition. Okay, here we go. All right, so now off we go. You can see this is going to take us a while to get to 1,000. Let's see how fast we're going here. Well, it'll take us a little while, but let's carry on. Okay, we can see that we now have pretty much every individual that's keeping at least 1 foot on the ground, and we've stalled out now at generation 112. So now, at this point, it's impossible for it's impossible for the algorithm to find a pair of individuals where one dominates the other. Okay. Let's make one final change. Let's go back to individual.py. Let's go back to dominates. You can see that we're pretty strict about determining domination. One individual has to be better in both objectives. What about softening this a little bit to greater than or equal to? So what this says now is that self will dominate other if it's faster and is at least as stable as the other. Okay. So we could see that most of them get a stability of 500. So let's make this a little bit easier to dominate, for one individual to dominate another. And now we won't stall out now because it's easier for the algorithm to find pairs of individuals where one dominates the other. Okay, so now we can sort of see that every individual in the population is more or less stable according to our definition of stability, and slowly but surely speed is increasing. There's a 1.149, 142, 1.16, not bad. All right, remember we're counting up to 1,000. Here's someone who's quite fast. Oh, 1.68, 1.168, 498, pretty good. 1.185, 193. Now we're really moving. So now we're getting some robots that are very fast and they're keeping at least 1 foot on the ground at all times. Okay, I think we're just about there. We've got someone who's at 0.2 now and 497. So now we're really getting something that's moving quickly. Okay, so when we play the winner in a moment now, we should see that it keeps at least 1 foot on the ground at all times and moves relatively fast. All right, it keeps at least 1 foot on the ground at all times. Not bad. Let's try it again and see what we get. One of the things you'll notice as this is running, remember that whenever an individual produces an offspring, that offspring inherits the same ID number as the parent. So you'll notice at this point there are sort of a number of species at work here. Species number 14, there's a lot of them in the population. 42 still exists. There's an individual, a descendant of the original robot that had an ID of 0. Let's see, here's an 11 left over. So what's happening is, although the robots are getting a little bit faster and a little bit more stable, we're losing diversity in the population. They're becoming more similar to one another. So next week in office hours, I'm going to make another change to our multi-objective optimization algorithm that will try and maintain diversity in our population as well. So instead of converging to variations of robot 14, we're going to use one of the objectives is not going to be speed or stability, but instead is going to be novelty. How new is the robot? How different is the robot compared to all the other robots in the population? And that should guard against what's happening here, which is that you can see that species 14 is sort of driving all the other individuals to extinction. You can see actually where's our fastest one here. 42 actually looks like the fastest at the moment, or 0. Okay, let's see what we get here. Before I run this, let's go through this. So 1.165 looks like the best. Oh, no. Individual down here from species 16, a little bit less stable than the individuals from species 14. That's why it's never able to dominate them, but it is definitely much faster. Let's see how this one does. Okay, well, this definitely makes a lot more sense. And we get a robot that's no longer jumping or flipping over, which was our original goal. So I think we'll stop there today. We've implemented multi-objective optimization now, which is determining who dies and who produces offspring based on speed and stability. And next week, I will talk about using this idea of multi-objective optimization to preserve diversity in the population. All right, until then, happy coding.